Oh boy, look what we have here. We have this very evil integral here. Now, I also realized MIT had a typo here. Their answer sheet says similar, but they missed a negative sign on one of the terms. So the answer on MIT is incorrect for this integral. So now before I show the solution, well, I mean technically I will, but for all these intermediate and advanced speed integrators who are watching, let's have a race. How fast can you solve this integral here? All right, I'll race with you. Ready? Get set, go. So we have what this is going to be from 0 to 1. Let's see. This is, I'm going to need to separate all this. It's 2. It's 2. Oh, I technically already know what my intentions are. So here I have negative infinity to 0. Okay. Here I have what? This is 2. I'm going to be very careful. Okay. This is pi. Oh no, it's not pi root 2. 2 root 2. Oh, I almost messed up. This is root 2 inverse tanh t over 2 to infinity. Infinity is going to, if you think of it in logarithm terms, it's going to be 1. So we're going to have inverse tangent of root 2. Is that acceptable? I don't think that's acceptable because that's complex. ln root 2. Oh shoot. 1 plus root 2, 1 minus root 2. Absolute value. Oh, okay. Oh, no. 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 If you beat me, congratulations. You cannot put your answer in inverse tanh form, I realized. That's how evil this integral is. Okay, you cannot leave it like this. If you left your answer like this, you would have been judged as incorrect because this is a complex number. So I had to put it in logarithm form. Okay, this is the real form. All right, so I hope you got this correctly, not in inverse tanh form. And what else? Yeah, if you beat me and you got this, that's very good. You are at a very good advanced level, because speed solving this is not easy to do. Okay, it takes a lot of accuracy and a lot of practice. Okay, so how do you actually solve this? For those who have not seen this, how do you actually speed solve this? So what you do, if you ever see this, because this is a very popular integral, so if you ever come across this, this is exactly what you need to do. You let you pretty much do a force u substitution. So let u equal everything. Let u equal square root of tan x. Then u square is equal to tangent x. Derive both sides, you get 2u du, and you get secant square dx. Now, the thing is, secant square is equal to 1 plus tangent square. But what is tan x equal to? U square. So secant square is equal to 1 plus u4. So what you actually have is 2u du, 1 plus u fourth equal to dx. And that's what you're going to substitute in. Okay? So your integral, plugging in the bounds, you get 0 to 1. Your whole integral should look like this. 2u squared over 1 plus u4 du. Okay? So you have this now. Now, for those who are new to my channel, you should probably take a look at a video that I made called the square technique, because that's what we're going to do right now. So it may look a little fuzzy to you, but if there's a point where you don't understand, I think it's better because I have a full explanation on the square technique in that video. It's somewhere in, I think it's an intermediate integration B training. So here you divide u squared to top and bottom, and that 2 is crucial. Okay, this 2 is very crucial. We're going to use that 2. So now we have u squared plus 1 over u squared. Now that 2, we're going to turn that into 1 plus 1. We're going to turn this into 1 plus 1. And pretty much what's going to happen is we're going to use 1 plus 1, and we're going to do 1 plus 1 over u squared minus 1 over u squared, a 0 substitution. Why are we doing this? Because u squared plus 1 over u squared, there are 2 different forms that we can actually put it in. U minus 1 over u squared plus 2, and u plus 1 over u minus 2. How do we know which one goes which? It's because we're going to do a u substitution. If this is my dw, right? Then what does my w need to be? Integrate this. What is this? The integral of this is u minus 1 over u. Okay? And look at that. I got u minus 1 over u. That's exactly how it's supposed to be. And so this, the other way, similar procedure. You know, if my dw is this, then my w needs to be this. Okay? So now when I do the u substitutions, I now get, let's see, plug in 0, I get negative infinity. Plug in 1, I get 0. So my dw is w squared plus 2 from negative infinity to 0. And now, same here, I'll use dt on this. dt t squared minus 2. Plug in 0, I get, it's not 0. Plug in 0 here, I get infinity. Plug in 1 here, I get 2. Okay, this is actually fine because the true form of arctange is actually this way. Okay, this is the true form of inverse tangent. Okay, it needs to be constant minus x squared. Okay, so that means that this would be like a negative arctange, but that's good because that negative could reciprocate this. So that's a good thing. So don't freak out when this happens. Just don't freak out. Okay, do not freak out when you see this. All right, nothing bad happened. Okay, so now we see, well, this is easy to solve. This is inverse tangent over root 2, right? So this is 1 over root 2 arctan of w over root 2. Plug in 0, 0, plug in negative infinity, pi over 2 times 1 over root 2. So we get pi over 2 root 2. And then we have the minus. Oh, I'm sorry. The minus gets canceled. Never mind. I'm sorry. Plus 1 over root 2 inverse tangent of t over root 2 from infinity. I'm sorry, from 2 to infinity. Okay. Now, here's the difficulty. Okay. You cannot leave this as arctange of root 2 because that is a complex number. Okay. You didn't put any absolute values in. Okay. You didn't put any absolute values in. In fact, you can't. You can't leave it like this. Okay. That's also not correct. Okay. You cannot leave it like that. That's still incorrect. That's still a complex number. Okay. So you cannot leave it as complex numbers. What you have to do, we know infinity is going to be 0. So then what we have here, inverse tangent is equal to 1/2 of the ln of 1 plus, and then x is going to plug in 2, you get root 2. 1 minus root 2. Okay, so as a reminder, inverse tanh, okay, should know the logarithm. It's very good to know the logarithm of this. This is equal to half of ln of 1 plus x over 1 minus x. Okay, how do I memorize this? I just remembered, the only thing I remembered was, don't forget the half. Okay, I learned this the hard way. I got a lot of mistakes. I got a lot of incorrect answers because I keep missing that god dang half. And then inverse tanh of 1 is undefined. Right, so that's how you know, oh, 1 minus x is at the bottom, because inverse tanh of 1 is undefined. Okay, so now that we know that, okay, now as you can see, 1 minus root 2 is a negative. Okay, this is where the complex, that's where the complex number comes from, because ln of a negative number is complex. Well, you can't have a negative number in a logarithm at all, but it's the freaking complex analysis argument thing. But in general, it becomes a complex number. So that's why we have this very hidden absolute value inside of arctangent. So this absolute value would just turn this around, okay? And then note that 1 over, let me rewrite this. So our actual answer, we have 2 root 2, not inverse tanh, we can't write it like that, ln of root 2 plus 1 over root 2 minus 1. Now the absolute value disappears. And note that, let me put another note here, 1 over root 2 minus 1 is equal to root 2 plus 1 if you conjugate it. So we actually have a square, and that square cancels out this 2. So our actual answer is pi over 2 root 2 minus 1 over root 2 ln of square root of 2 plus 1. Okay? In the MIT answer sheet, they had a plus, and that's incorrect. Okay, they messed up somewhere. I believe they messed up somewhere. They messed up here. Whoever was writing the answer sheet, they messed up somewhere here. Okay, this is the tricky line, here and here, right? Inverse tanh, you cannot write it like that because that's a complex number. You need to write everything in real form. So you're forced to put it in logarithm and then use the absolute value. Okay, so be very careful. This integral is very evil. Not only the solving it elementary was very hard to see, but the bounds, like 0 to pi over 4, is already evil enough. That pi over 4 was the devastating of all of this bound computing. Okay, so your answer should be a minus 1 over root 2 ln of root 2 plus 1. Okay? Alright, holy hell. Go practice that integral before your integration bee throws this at you. Alright? Cool. Hope that helps. I'll see you guys in the next video.